Hello everyone, today in this video we'll be discussing the second module of data communication, which has to do with conversions. Okay, so in the first topic we'll be looking the digital signal to digital data conversion, and in the second topic we'll be discussing about the transmission modes, and in the last topic we'll be discussing about digital to analog conversion. Okay, make sure you watch the video till the end because there are many subtopics and it's hard to understand the next topic if you don't understand the previous one. Okay, and if you like this video, hit the like button and don't forget to subscribe to my channel. Okay, the first topic is digital to digital conversion. This is about digital data to digital signal conversion. Okay, so here what we are doing is data can be either analog or digital. Okay, analog means the normal signals here, and digital signal means either 1 or 0. Okay, this type of signal is known as digital, and this is analog signal. Okay, data can be represented in either of these forms. Okay, now signal can also be either of the forms of analog or digital. Okay, as I mentioned earlier, so we have two things. First one is encoding and second is decoding. See here, the computer has the digital data in the form of bits. When we have to send the data through a link, at that time we have to convert this data into the digital signal or analog signal. Here we will be focusing about on the digital signal. Okay, so we'll be using encoding to convert the digital data to digital signal. Okay, and the decoder will decode the digital signal to digital data. Okay, we'll be focusing on encoding part here. Now, what is the process called? It's called as line encoding, which means it's the process of converting digital data to digital signals. Okay, so here there are some of the characteristics which we need to know very thoroughly before moving on to the next topics. Okay, so listen very carefully. What's the difference between data element and signal element? See, what's a data element? Suppose we have a bit a group of bits here, 1 0 1 1 0 1. Okay, so a data element is the smallest piece of information, which is a single bit. This is known as data element. This is also a data element. Okay, this is also a data element. Now if I make a group of this and consider this as a single element, that's known as signal element. So a piece of information is known as data element, and the group of the bits is known as signal element. Okay, after knowing about the difference between each of these, let's understand what is the ratio R. Ratio R is very important. It comes a lot of time in the numericals. Okay, ratio R is the number of data elements per signal element. As I told earlier, as I told in the example, the group of bits, how many bits will be considered as a single signal element, that much is the ratio R. Okay, number of bits, which is in this case 1 2 3 4 5 and 6. So if this is considered as a single signal element, okay, then the ratio will be 6 by 1, which is 6. Okay, so let's see some cases here. See here, in the first case the data is 1 0 1. This is one data element, and if I consider this as a single signal element, at that time the ratio will be 1 by 1. Okay, in the second case I have two signal elements for representing one data element. At that time one data element divided by two signal element, R will be 1 by 2. Okay, in the third case two data element are there which is represented by one signal element, so therefore the R will be 2. In this case there are 4 data elements and 3 signal elements, so R will be 4 by 3. Okay, so this is all about the ratio and the difference between data element and signal element. The next one is you need to know what is data rate and signal rate. Okay, data rate, as the name suggests, is the amount of the data transferred per second. Okay, so if I have 3 bits which is getting transferred per second, that's known as the data rate, which is 3. Okay, 3 is the data rate. Signal rate means how many signals are getting transferred. So suppose that there are 3 signals which is having the data 110 111 001. Okay, so in this case one signal element, second one, third one, 3 signal elements are getting transferred. That's known as signal rate. Those are also known as bit rate and baud rate. Okay, now how to increase the efficiency of the transmission? Suppose that consider an example of road. Okay, in the road you have cars, right? And inside the cars there are people. So to reduce the traffic, you need lesser number of cars and more number of people per car. Okay, so suppose that there are 3 cars here, and the number of people getting transferred is from point A to point B. So to reduce the traffic, you have to transport the maximum number of people per car. Okay, then the traffic will be reduced. Consider the people as bits here. Okay, in our case it's bits and the cars as signals. Okay, so what we have to do is we have to reduce the signals getting transferred, which will decrease the bandwidth requirement, and increasing the data rate means increasing more bits sent per second will cause the transmission of more bits in a lesser amount of time. Okay, so that's all about the data rate and signal rate, and there is a formula for it. See here, what was the ratio R? R was equal to number of bits transferred divided by signal elements. How many signal elements are there? Okay, so n by s is equal to R. From here, what's the value of s? If I shift s here, it will become s is equal to n by r. Okay, and c is a factor which depends on each case. Okay, so it's a factor getting multiplied here, and rest of the formula is same. Okay, bandwidth is nothing but the amount of data getting transferred per second. Okay, this same as the bit rate, but this slight difference here will be including the signal also here. See here, signals carry the data. The more a signal can carry, the more data will be transferred. So bandwidth is how many times a signal is getting transferred per second. See here, this one signal here, this another one. So many signals are getting transferred per second. Okay, so each signal will have a group of data here. So what we can do, increase the amount of data per signal and reduce the number of signals. So in that case, the bandwidth required will be reduced. So it will be like lesser amount of frequency, it can transfer more data. Okay, so only one signal is required per second, and each signal will have larger amount of data. Okay, so that will make the data transfer more efficient. So bandwidth is nothing but how many signals can be transferred per second. Okay, this one signal, this another one, so like that how many can be transferred in a single second is called as bandwidth. Okay, it's also known as the range of frequencies supported. Okay, the formula of bandwidth is also same as the previous one, which is C into N into 1 by R. Okay, same as for the signal rate, because it gives the number of signal elements getting transferred in 1 second. Okay, the next one is baseline wandering. This means while decoding, the average power is calculated. Okay, suppose that the voltages received are high and low alternatively. Okay, so in this case the average power will be calculated, and this power is measured. See here, this is the average power. Okay, and the next incoming signal is lesser than the average power, that means it's a 0 bit. If it's higher than the average power, it means it's a 1 bit. In that way the receiver decodes if it's a higher bit or lower bit. Okay, so sometimes what happens is a long strings of zeros and ones can cause the drift in baseline, means at that time the average power is difficult to be calculated, because it there will be no difference, means when is the bit ending and when is the bit starting. If there is a long string of zeros, at that time the receiver won't know exactly where the bit gets end and how many zeros are sent. Okay, so that can cause drift in baseline. So that is known as baseline wandering. Okay, the next one is DC components. DC means direct current. See what happens in direct current, there will be no frequency. So if a current is getting transferred here, it will be constant all over the time. So sometimes what happens is the voltage which is getting transferred from the sender to the receiver remains constant for some amount of time. So what can happen is it can become like a constant current. So some telephone lines do not support frequencies less than 200 Hertz. So when it becomes constant, the frequency starts to reduce, and when it reaches below 200, the transmission of the data cannot take place in telephone lines. The next one is built-in error detection. This means there should be some technique in the transmission process to detect if there are any errors that and they have to be corrected by itself. Okay, so there should be built-in error detection and correction service. Okay, the next one is self synchronization. What do you understand by the term synchronization? That means between the receiver and the sender, the speed should be synchronized. Means whatever speed it's sending, that should be the same speed of receiving. Otherwise there can cause faulty interpretation of the data sent. For example, see here, this is the data sent 1, then 0, then 1, 1, 0, 0, 0 and 1. But in the receiver's side, the receiving data is twice as fast as the sending data. So what happens is, while this data is sent as 1, the receiver thinks that 2 times the 1 is sent. Okay, this is the first bit and this is the second bit. So in that way, the received data will be different than the sent data. Okay, because of lack of synchronization. So it's very important to synchronize the speed between the sender and the receiver to ensure the correct transmission of the data. Okay, the next one is immunity to noise and interface. That means the code should be immune to noise and other interferences. Okay, to avoid the errors. Okay, the next one is complexity. Means there are many schemes to transmit the data, and the less complex the scheme is, the cheaper and the simpler it is to maintain. Okay, let's look at some of the numericals. So in this numerical, we have been asked to a signal carrying data in which one data element is encoded as one signal. That means if this is the signal, only one data element is there in each signal. So that means R is equal to 1 by 1, which is 1. Okay, R is 1. If the bit rate is 100 kilobyte per second, what is the average value of baud rate? Baud rate is nothing but signal rate and bit rate is nothing but data rate. Okay, so by using the formula, firstly we'll calculate what is C. Since we have to find out the average between 1 and 0, we can take as 0 plus 1 by 2. So C will be 1 by 2, and then the baud rate, which is the signal rate, can be calculated as S average is equal to C into N into 1 by R. C is 1 by 2, N is 100 kilobyte per second, so it will be 100 into 1000, and R is given as 1. Okay, so applying the values in the main equation, we'll get the answer as 50 kilobaud. Okay, in the next question, we have been given that the receiver's clock is 0.1% faster than the sender's clock. So there's a lack of synchronization here, and the receiver clock is 0.1% faster than the sender's clock. What is the how many extra bits does the receiver receive if the data rate is 1 kilobyte per second in the first case, and in the second case 1 MB per second? Okay, so let's see one case, each case one by one. Suppose that, see here, the sender is sending 1000 bits in 1 second. Okay, but the receiver's clock is 0.1% faster. So what's 0.1% of 1000? That's equal to 1. So it's receiving 1 bit extra per second. Okay, so it's receiving 1 extra bit. So it's receiving 1 extra bit per second. Okay, similarly, in the next question we have been given that how many extra bits are received if the data rate is 1 MB per second? 1 MB means 10 raised to 6, which is 1 followed by 6 zeros. Okay, now since it's 0.1% faster, we'll be finding how many extra bits are there into 0.1%. Okay, so that will give us 1000. So 1000 extra bits are received in the second case. Okay, in the first case it's 1 extra bit, and in the second case it is 1000 extra bits. Okay, discuss about line coding schemes. That means digital data will be given. We have to make a digital signal out of it. Okay, you have to draw a digital signal out of it. Let's see how to do that. There are 3 ways: unipolar, polar and bipolar. Let's discuss one by one each of these. In unipolar scheme, the positive voltage is considered as 1 bit and 0 voltage is considered as 0 bit. Okay, so the data is given here and our task is to make a waveform. Okay, so by using this data 1 0 1 1 0, we'll be making a wave. Okay, so initially we'll be drawing the y-axis and x-axis, and after that the first bit is 1. 1 means positive voltage. I'll start from here as a positive voltage. Then next is 0. I'll go down and to the x-axis, and then the next bit is 1, so it's positive voltage. Then next bit is 1, it's same as positive voltage. Then next bit is 0, I'll come down to the x-axis. Okay, so this is the digital wave under the unipolar scheme. Okay. The next one is polar scheme. In polar scheme we have three types: NRZ, RZ and biphase. Okay. So let's discuss the NRZ scheme. In this, remember, negative voltage is 1 bit and positive voltage is 0 bit. It's the reverse as the previous one, in which positive was 1, here negative is 1. Okay. So let's see the first one, NRZ. We have two versions, we have two types. First one is NRZ level, and in NRZ level what we will do is, this is the same thing, positive voltage as 0 volt, negative as 1 bit. This is the same as the previous one, and if the data given is 0 1 0 0 1 1 0, how can we represent using NRZ L scheme? Okay. So see here, if it's a 0 bit, make it as positive volt. If it's 1 bit, make it as negative volt. Okay, simple. See here, 0 bit is positive volt. When it's 1 bit, make it as negative volt, then 0 positive volt, then again 0, it remains positive volt, then negative volts for 3 1 and positive volt. Okay. So this is the NRZ L scheme. Coming to NRZ I scheme, it's a bit different. In this we will invert only when the next bit is 1. So see here, if the data given is 0 1 0 0 1 1 and 0, in NRZ I scheme what we do is, we will start from 0 at the top. 0 is considered as positive voltage, so we will start from here and we will see the next bit, it's 1. Whenever it is 1, we have to invert, means come down to negative. Okay. Then we will see the next bit here, it's 0, continue in the same form, it's 0, continue in the same form, and next bit is 1. Whenever it is 1, invert the value, come up, and see here next bit is 1, come down, and see here next bit is 1, come up, and continue, next bit is 0. Okay. So this is the way to represent the digital wave in NRZ I scheme. Okay. This was about the polar scheme under NRZ. The next one is RZ scheme. In RZ scheme we return to 0. That means in the previous ones we were not returning to 0. See here, we are just either positive or negative. Okay, we were in the positive end or negative end. Here we are not transitioning, but in this case will transition in between the bit and return to 0. Okay. So if the data given is 0 1 0 0 1, how can we encode using RZ scheme? See here, bit 0 is represented as from negative voltage to 0. Okay. Finally it should return to 0 if it's 1 or 0. Okay. In both cases we have to return to 0 here for both bit 0 and bit 1. So in bit 0 we will start from the negative, come to 0. In the bit 1 we will start from positive, come to 0. Okay. So by using these two patterns we will draw the waveform. See here, wherever you find bit 0, at that place draw the same pattern from negative to 0. In bit 1 draw this pattern. Okay, like that do for all, and after that finally we have to join the marking points. Okay, like this one, this one, this one and this one. Okay, that's the whole waveform. That's for RZ scheme. And coming to the third one, which is biphase, we have two types, Manchester and differential Manchester. Let's see one by one. What is Manchester? Manchester is the combination of NRZL and RZ schemes. Okay, suppose that the data given is 0 1 0 0 1 1. So the pattern for 0 is this one. Remember this pattern for Manchester, it's from top to low. 0 is defined as from top to low and 1 is defined as low to high. Now by using this, divide the time axis into the bits, and wherever you find 0, make this pattern from top to low, and wherever you find 1, make this pattern. Okay, that's it. After that, if we find any gaps in between, join these two, and that will give us the Manchester encoding digital wave. Okay. Similarly, we have the next one, which is differential Manchester. Is the combination of NRZI and RZ scheme. Okay. So here what we do is invert only when next bit is 0. In the previous one what we did, invert only when next bit is 1. Here we will be inverting when next bit is 0. So if the given data is 0, 1, 0, 0, 1, 1, what we will be doing is we will be starting from here, we will be coming to here, we will be checking the next bit 1. If it's 1, don't invert, continue here, okay. Then come to here and check next bit is 0. If it's 0, don't continue, go up. Then come here and then it's 0, again go up, okay. Then it's 1, don't do anything, continue, and come here. If it's 1, continue. In between the bits we will be moving up or down. This is the between the bits, okay. In each bit we will be moving up and down, okay. See here, in between each bits we are moving up or down, okay. But in between two bits we are moving only when next bit is 0. See here, next bit is 1, so we are not moving here. And whenever the next bit is 0, in between this, see, the next bit of this is 0, so we are moving in between the bits, okay. Here and here, and here we are not moving because the next bit is 1, and here also we are not moving because next bit is 1, okay. So in between bits we will always move, and wherever it is, so in the same bit we will move always, so inside the same bit we will move, whereas in between two bits we will move only when the next bit is 0, okay. So this is about the differential Manchester under the bipolar scheme. The first two are over, unipolar and polar. Let's see about bipolar. Bipolar scheme is very simple. We have 3 levels: positive, negative and 0, okay. There are 2 types, AMI and pseudo ternary. Let's see one by one. In AMI, the 0 bit is 0 voltage and 1 bit is alternating between positive and negative voltage, okay. Let's see how it is. If the data given is 0 1, 0 0, 1 0, at that time 0 is 0 voltage, so we will be starting from here, and next 1 bit is alternating between positive and negative. So first 1 bit will be positive, then 0 is at the 0 axis, and when we encounter the second one it will go to negative, okay. If we have another one here, it will come here and go to positive. So 1 will be alternating between positive and negative, okay. That's the AMI. Pseudo ternary is the opposite of that. 0 will be alternating, whereas 1 will be constant, okay. So 0 is starting from here, positive, 1 will be at 0, and 0 will be becoming negative, then positive, 1 will be at 0, and 0 will become negative. So first 0 is positive, second 0 is negative, third is positive, fourth is negative, okay. So this is about the bipolar, pseudo ternary, and this is all about the line coding schemes. Let's move on to the next topic. In topic, which is analog to digital conversion, we will be converting the analog signal given to us to a digital data, okay. So for that we will be using a technique called pulse code modulation, okay. So in this technique what we will be doing is we will have 3 process: sampling, quantization and encoding. So let's see the overall process. First we will have the analog signal here, and it will pass to the sampling process. What does sampling do? Observe here carefully. The given wave is in this form, and for each interval what we'll be doing, we'll be marking the point in the analog signal. So we'll get figure something like this, okay, for each point when we mark here. Then after that we need to get the numeric values for the marked points. So we'll making a graph here and marking some numbers here, and by using these numbers we'll be converting it into the binary form to get the digital code, okay. So we'll be discussing each of these 3 steps in detail, okay. So let's get started with the first one, which is sampling. In sampling, it's the conversion of the continuous analog signal, which is the analog signal here, to the discrete digital signal known as sampling, okay. When you convert it into the discrete form in this way, it's known as sampling. Pulses from the analog signal are sampled every t second, okay. For each interval we are sampling, okay. For small intervals we are checking where the analog signal is and we are marking the points, okay. This period is known as sampling period. Similarly, frequency of sampling is in 1 second how many samples are performed. Suppose that in 1 second we are checking 5 times and marking the points. At that time the frequency will be 5, okay. means in 1 second how many times the sampling is being performed, that's the frequency. Okay, there are three sampling methods. First one is ideal sampling. In ideal sampling we will be marking the points in the main wave, in the analog wave, and that's known as ideal sampling. And in natural sampling we'll be marking a interval, okay, and we'll be connecting the points here. Okay, so we'll get a wave in this form with some intervals. Okay, this is natural sampling. And the third one is flat top sampling. This same as the natural sampling, but the difference is in flat top sampling will not be marking the wave from here, but we'll have a flat top. Okay, here also we'll have the flat top for each of the bar graph. Okay, so the advantage is that it removes the noise since the top is flat. Okay, how is that? See here, even if there's a disturbance here, that won't be reflected here since the top is flat. But in this case the noise will be reflected since the changes here will be marked as such. Okay, so in natural sampling it's having a lesser advantage than the flat top sampling in removal of noise. Okay, after knowing about what sampling, let's talk about sampling rate. According to Nyquist theorem, the sampling rate must be at least 2 times the highest frequency, not the bandwidth. Okay, let's understand this by an example. Consider an example here where the frequency minimum is 0 and the frequency max is here. Okay, now the low pass filter's bandwidth will be the difference between the maximum and the minimum frequency. So this is the bandwidth. And what's the sampling rate? Sampling rate means how many times the sample is happened per second. Okay, in 1 second how many times the sample is happened. So if this is 1 second, and how many times it's happened? 1, 2 and 3. Okay, 3 times. If the maximum frequency of the same wave is suppose if it's 1 second here, at that time if it's happening 6 times, okay, the frequency is 6, means the signal is changing 6 times in 1 second, and the sampling is just 3 times, so we'll miss out the remaining 3 times what was the change. Okay, so that's why the sampling rate should be more than the frequency max. Okay, so if the frequency max is 6 times, the sampling rate should be 2 times the maximum frequency, which is 12 times. So we can ensure that all the data is getting included in the sampling. Okay, so if it is 12 times, for each of the signal we will have 2 samplings. Okay, so if I zoom this here, it will be like for a single wave it will be like this. Okay, and it will be checked 2 times per second, so the sampling will be 2 times here, and you can get the accurate data for the first case. Okay, you can increase also, but minimum should be 2 times. Okay, so that's known as the sampling rate and Nyquist theorem. And if it's the band pass filter, at that time you can't use the bandwidth. Okay, because bandwidth will be less than the f max. See here, in this case bandwidth is same as the f max because f min is 0 and bandwidth means f max minus 0. So f max and bandwidth both are same, and you can use in the equation 2 times the bandwidth also. Okay, instead of f max. But here bandwidth is less than f max, so we can't use that. We have to use 2 into f max only. Okay, in case of band pass filter. After the sampling process, we need to get the numeric values of the points marked. For that, what we'll be doing is we'll be marking the maximum and the minimum voltage, and after that we are writing some numbers here which are the quantization levels. Means if you want if you have 3 bits data, in this signal we have considered 3 bits of data to be transferred. Okay, for representing 3 bits we need 8 levels, right? Like 0, 0, 0, 0, 0, 1, like that we need 8 possibilities, so we need 8 levels. So I have marked from 0 to 7, which are nothing but the decimal equivalents of the binary values, and after that I'll be marking the points at each intervals. Okay, this is the point here, first, second one, third one, and so on. Okay, after marking this I'll be seeing each point where it is lying to. This point is lying closest to 2. Okay, like that this point is lying closest to 5, the third point is lying to 6. Okay, like that I'll be marking all the points and checking which level it is lying closest to. After knowing all those numbers, I'll be writing down here the closest points, and I'll be converting those points to binary values. Okay, and this is nothing but the digital code. All right, if I have the digital data, how do I convert this data into a signal? So for that, what we'll do is, for each binary value, I'll get the decimal value here, and I know the sampling time. So for each of the sampling time, I'll mark the points which are first 2, then 5, then 7, so like that and so on. I'll mark for each of the points at the sampling times. Okay, for each interval I'll mark the points, and I'll join the points to get the analog signal. Okay, so that's what we do in decoding. Encoding is the process of converting the analog signal to digital data, and decoding is the process of converting digital data to analog signal. Okay, and the last step is encoding, which has some formulas, like by using these formulas we can get the number of bits transferred and the bit rate. Okay, so see here, quantization level means how many levels we divide into. See here, in this case the quantization level is 8. Okay, since we have 3 bits, to represent 3 bits we need 2 power 3 levels. Okay, 8 levels. So that's the same formula here. If you have n bit words, we need 2 power n levels. Okay, and bitrate is given by, bitrate means how many bits are transferred, sampling rate into number of bits per sample. Okay, so see here, if this is the wave here, and sampling rate means in 1 second, if it's 3 times, sampling rate is 3, and number of bits per sample, for each sample if it's 5 bits, so 5 into 3 will give me the total number of bits transferred in 1 second. Okay, so that's the bit rate. Let's see some numericals. The first one is, a complex low pass signal has bandwidth of 200 kilohertz. What is the minimum sampling rate for signal? We have been given with bandwidth, which is of low pass, so bandwidth is equal to f max. See here, for a low pass signal, bandwidth and f max are same. Okay, so we can use the Nyquist theorem as 2 into f max or 2 into bandwidth. That's only for the low pass signal. So in this question we will be using that formula, bandwidth is equal to f max is equal to 200 kilohertz. According to the Nyquist theorem, 2 into f max is 2 into bandwidth, which is 2 into 200 kilohertz, which is a sampling rate 400,000 samples per second. Okay, moving on, we have the similar question. We want to digitize human voice. What is the bit rate assuming the 8 bits per sample? So what's given is 8 bits per sample, it's the bit rate. Okay, so what's given is 8 bits per sample, and what we have to find out is bit rate. Okay, means how many bits are needed. Okay, so the human voice normally contains frequencies from 0 to 4000 hertz. So sampling rate is nothing but 2 times the maximum frequency. 2 times 4000 will give 8000 samples per second, and how many bits are there per sample? 8 bits. So total number of bits will be 8 bits into how many samples are there? 8000. So 64 kilobytes per second is the bit rate required for digitizing human voice. Okay, original sound recovery means decoding. We have the digital data here 101101 like that, and we have to convert the digital data into analog signal. For that we'll write the binary codes equivalent of this, means 101 is 5, 011 is 3, and here also 011 it's 3. Okay, we'll be holding the value at each interval. Okay, suppose that this is not the same graph for the data here. Consider an example here. If the data here is 2, okay, I'll be holding the point at 2 and till the next sample. If the next point is 5, suppose that the series is 2, 6, 8, 10 and 8, 4 like that. Okay, so the first, if this is the series here of the given data, so first point is 2, I'll be holding 2 till here, and when the next interval comes, the next point is 6, so I will join the point till the 6 here, then the next point is 8 at the next sample. So like that I'll keep on joining all the points till I get the whole graph here. Okay, so this is just a rough graph here. To make it more smoother, what I'll be using is a low pass filter. Okay, by using a low pass filter we can smoothen the curve and remove the noise. Okay, so I can get approximately the original wave as the analog one. Okay, pulse code modulation bandwidth. Bandwidth is having two types, digital and analog. In digital bandwidth, I mean number of bits transmitting per second. Okay, how to calculate that? See here, if this is the wave here, okay, this is the wave here, and we need to calculate the total number of bits. How many signals are there? First calculate that. Means in this case 4 signals are there, and in each signal how many bits are transmitted? Suppose that at each signal 3 bits are transmitted, then how many signals are there? 4. So 3 into 4 will give me the total number of bits transmitted, which is 12. Okay, so the range of frequencies, how many can be transmitted at a particular interval of time, is nothing but bandwidth. Okay, and analog bandwidth means number of signal changes per second. Means see here, how many times the signal is getting changed? 4 times, right, per second. So the frequency or the analog bandwidth is 4 hertz here. Okay, bandwidth has the same formula as the signal rate, which is C into N into 1 by R. Okay, now we know some formulas here. N is nothing but the bit rate, which is NB into Fs. NB means number of bits per sample, and Fs means how many times the sample is changing. So when we multiply the number of bits per sample and how many samples per second, we'll get the number of bits per second. NB into Fs will give me the number of bits transmitted per second. Okay, so applying that value here, and what's the value of Fs? Fs is nothing but sampling rate. Okay, sampling rate is defined as 2 times bandwidth for low pass signal. Okay, so I'll be using that value here, 2 times bandwidth of analog, and then consider a case where C is equal to 1 by 2 in average case, and R is 1. R is 1 means each signal element just has one data. Okay, in that case number of data elements divided by the number of signal element will be R is equal to 1 by 1. Okay, so R is 1 and C is 1 by 2. When we apply the values here, we'll get the digital bandwidth as NB into analog bandwidth. Okay, that's nothing but number of bits per signal, which is NB, into number of signals, which is analog bandwidth. Okay, number of signals per second. Okay, so when we multiply it, we'll get the number of bits per second. Okay, so the number of bits per second is the digital bandwidth. Okay, the formula of maximum data rate of a channel is calculated as follows. What is maximum data rate? Means the how much data can be transferred at max. Number of bits transferred is equal to number of bits per sample into number of samples per second. When we multiply it, we'll get the total number of bits transmitted per second. Okay, so here's the formula of number of bits transmitted, and number of samples per second is Fs. Okay, so what is log base to L? See here, L is the number of levels. In the previous example where I considered 8 levels, right, for the quantization process, 8 level means 2 cube. So by using log 8 base 2, we'll get the value 3. So that's the number of bits getting transferred. In that case, we had 111, 101, like that, right? 3 bits. So by using that, by using the formula log L base 2, we can find out the number of bits and into Fs. Fs is the sampling rate, which is 2 times the bandwidth. Okay, so by using this formula, we can find out the total number of bits transmitted. Okay, and in case the total number of bits transferred is given, we have to find out the bandwidth. We can keep bandwidth here and transfer log L and 2 in the denominator of N max. Okay, so we'll get B min as N by 2 times log L. Okay, see, parallel is nothing but the parallel transmission of the bits. Means if you have to transmit n bits, we need n wires. Okay, so those all will be transmitted at a single time. Okay, so that's parallel transmission. And serial transmission means only one wire will be there and each bit will be transferred one by one. Okay, and we have 3 types. First one is asynchronous, means prior to the data transfer, both the sender and the receiver will agree on the info to be exchanged. So for example, the info will be sent in this form. The starting bit and the ending bit will be specified. So when the data is sent from the starting bit, it is received by the receiver, and when the ending bit reaches, at that time the receiver will stop receiving. So in that way we can have the gaps in between, and for each of the group each of the group of bits, the starting and the ending bit should be 0 and 1. Okay, so that's asynchronous. And in synchronous there will be no pattern, but there will be frames. Okay, so each frame will be sent in a particular amount of time, like interval of time. So for that particular interval of time, the receiver will receive the data. Okay, so that's synchronous transmission. And isochronous transmission is also same as the synchronous transmission, but in isochronous we have more ensurety of the safe transfer of the data, because the synchronization between only the bits is not enough. The entire stream of bits should be synchronized. Okay, so the entire stream of bits should be synchronized. Okay, let's talk about digital to analog conversion. That means we have the data here in the form of bits. This we are converting into the analog signal. Okay, so we have some factors here in the conversion. See here, wave is defined by 3 parameters: amplitude, frequency and phase. Okay, amplitude means how much high the wave is, means the max and the min points, and frequency means how much the wave is having the frequency, means this is more frequent than this wave. Okay, so per second how much times the wave is changing, that's the frequency. And the phase is what's the angle here. See here, while the wave is starting from here, what's the angle? Okay, that's the phase. If a wave is starting from here, it will be 90 degree. If it's starting from here, it will be 180 degree. Okay, like that, that's known as phase. Okay, so in digital to analog conversion, we'll be altering the values of amplitude, frequency, phase. These three values will be altering to change the signal. Okay, why will be altering? Because we have different data elements, right? Like 1 0 1 1 0 1, like that. To correspond to the changing of the bits, we have to make the corresponding changes in the wave also. Okay, so for the changes we can use the 3 methods: amplitude, frequency or phase. The last one, which is quadrature amplitude modulation, is the combination of the first one, which is amplitude, and the third one, which is phase. Okay, so we'll be discussing each in detail one by one. Okay, before that we need to recap what we had learned earlier, means the difference between data element and signal element. What is the data element? So suppose that this is the data which is given to us. The single bit is known as data element and the group of data is known as signal element. Okay, and what is our data rate and signal rate? Data rate means how much data is sent per second. Okay, that's known as data rate. And signal rate means how many signals are sent. Suppose that we have many groups of data here. So in this case, if 3 signals are sent, 1 2 3, at that time the signal rate will be 3 signal rate per second. Okay, and the third one is carrier signal. It means before transferring the data from the sender, what we will do is we'll send a high frequency wave which will be synchronized with the receiver. After this is established, then we will make corresponding changes with respect to the data. Okay, so if it is 1, we will either change the amplitude or frequency or the phase. Okay, then if the next bit is 0, we'll make the corresponding changes. So first what we establish here is a high frequency wave, which is the carrier wave. Okay, it's also called as base signal or carrier signal. The fourth one is the bandwidth. Bandwidth means how much data is getting transferred per second. Okay, so if you have to transfer a large amount of data, we need a greater bandwidth, and it's also defined as the range of frequencies supported by the transmission signal. Okay, so this is the F min, minimum frequency, and this is the F max. The difference between the F max and F min will give me the bandwidth. Okay, so it can be defined as the data supported, means how much data can be transmitted per second, and how much frequencies can be transmitted per second. Okay, that's known as bandwidth. Okay, let's look at some numericals. In the first question we have been asked, an analog signal carries 4 bits per signal element. That means 4 bits per signal element. That means R is equal to 4. If 1000 signal elements are sent per second, this is the signal rate 1000. Okay, and find the bit rate. We have to find out what's the value of n. So by using the formula S is equal to n into 1 by R, the value of S and R is known. So by using these two values, we can find out the value of n. Okay, n will be equal to S into R, which is 4000 bits per second. Okay, in the second question we have been given the bit rate, which is 8000. That's nothing but n, and baud rate, which is S, that's the signal rate which is 1000. How many data elements are carried by each signal element? Means you have to calculate the value of R, number of data elements per signal element. Okay, we have to calculate R, and in the next one we have to calculate how many signal elements do we need. Okay, so to transfer all the data means a large group of data, it will be divided into many parts. How many parts are needed for transferring the data? Okay, that's nothing but the number of signal elements. So let's see, by using the formula S is equal to N into 1 by R, we can calculate the value of R, which is 8 bits per signal element. Okay, means for each signal element we have 8 bits. Okay, 8 group of bits will be transferred by a single signal element. Okay, next we have to calculate how many levels are required. Levels means how many signal elements. See here, suppose that we have to transfer 3 bits. Okay, so it can be 0 0 0 0 0 1 like that till 1 1 1. So how many combinations are there? Total 8 combinations. Okay, so for 3 bits we have 8 combinations. Now we have 8 bits here. 8 bits are to be transferred, means the total number of combinations will be like 8 times 0 till 8 times 1. Okay, so total number of combination will be 2 power 8, which is 256. Okay, these are the total number of levels or the signal elements needed for representing the particular bit. Okay, so you can use this formula. R is equal to log L base 2. You have to find out the value of L. It will be 2 power R. 2 power 8 is 256. Okay, so this many signal elements are needed for supporting the transmission. Okay, amplitude shift keying. In this we will be altering the amplitude to represent different signal elements. Okay, so this is why it's called amplitude shift keying, and both the frequency and the phase remain constant, so we are just altering the amplitude. Binary ASK means we have two things, 1 and 0. So suppose that this is the data here which you have to transfer it to analog. Okay, so what we'll be doing, whenever we get a 1 here, we will be making the amplitude high, and whenever we get 0, we are lowering the amplitude. Okay, so in that we will get a signal of this type. All right, so the carrier frequency, this is the carrier signal, and we'll be altering this signal by using the data given. So whenever it is 1, we will be making we'll be keeping it same. Whenever it's 0, at that time we will stop the frequency. Okay, so in that way we will get a wave, which is the digital which is the analog form of the data given. Okay, so this is a formula which you need to remember. B is equal to 1 plus D into S. Okay, see here, in this numerical we have been given the B as 100 kilohertz, and which spans from 200 to 300 kilohertz. Okay, so we have to find out the carrier frequency and the bit rate. Okay, so let's find out. B is given to be 100 kilohertz and D is given as 1. Okay, so D is just a case factor, like before we had C, right? Now here we have D. Okay, so we have to find out FC, which is the carrier frequency, and the bit rate. So let's see, carrier frequency can be any value between 200 and 300. So for instance, take 250. So that's the carrier frequency, and we have to find out what is N. So using the formula B is equal to 1 plus D into S, substitute the value of S as N by R. So by that you can find out N. Okay, R is 1, so we get the value of N as 50 kilobyte per second. Okay, talking about the frequency shift keying, we have to change the frequency only, and the amplitude and phase remain constant. Okay, so we have two types of frequencies for representing 1 and 0. For 1, F1 is used, and for 0, F2 is used. Okay, so let's see how it works. See here, if this is the data given, what is the change in frequency? See, this one type of frequency, this is one type of frequency, and this is another type of frequency. So the length between each signal is varied. Here that's known as frequency. So for zeros we will be using one type of frequency, and for 1 we will be using one type of frequency. Okay, so in that we will represent the given signal. Coming to numerical part, you have to remember this formula. It's same as that previous one, but here we will have 2 delta F. Delta F is nothing but the difference between two frequencies. Okay, F2 minus F1. All right, that is delta F, and we'll be multiplying that with the we'll be adding that with the main formula. So let's solve a numerical here. This is the same numerical as the previous one. 100 kilohertz is the bandwidth, and we have to find out the carrier frequency and the bit rate. Here we have to apply the same formula. We can choose the midpoint of carrier frequency as 250 kilohertz, and we have to choose 2 times delta F. See, 2 times delta F is nothing but whatever value they give here, bandwidth divided by 2. Okay, that is 50 kilohertz. Therefore, by applying those values, you will get the answer of N as 25 kilobytes per second. Okay, Here's another question in which we have been asked we need to send data of 3 bits at a time at a bit rate of 3 MB per second. See, we need to send 3 bits, means either it can be 000, 001 like that till 111. Okay, so how many levels we have here? 8 levels, right? So level will be 8 here, and what we need to find is calculate the number of levels at different frequencies. We have done that, the baud rate and the bandwidth. What is baud rate? Baud rate means at each signal element how many data elements will be carried. Okay, since it's given that we have to carry 3 bits at a time and the bit rate is given as 3 MB per second. See, 3 bits per 3 MB per second. Okay, so what will be for 1 bit? 1 bit will be 1 MB per second, right? So for each signal element there will be 1 MB per second, therefore 3 MB per second divided by 3 is 1 baud. Baud is used for signal rate. Okay, so we get the baud rate as 1 M, and the next question is to find out the bandwidth. Okay, bandwidth means how many range of frequencies are supported. See, we have to send 3 bits at a time, and in this one we have 8 levels, right? So 8 different kinds of frequencies we need from F0 to F7. So for representing 8 different frequencies with the carrier frequency as 10 megahertz, that means the mid frequency is 10 megahertz. Okay, we need 8 frequencies, the midpoint is 10 megahertz, and here you will have 4 frequencies, here you will have 4 frequencies. For each type of data, like 000, this will be used, and 001, then 010, like that. Okay, and you can have 1 megahertz difference or 2 megahertz difference. That depends upon you. You can set that, but you need to have the bandwidth as from 10 you have to have 4 in the left and 4 in the right. Okay, and one more thing, the bandwidth will be 6.5 minus 13.5. okay, that's the range of frequencies supported. Okay, to phase shift keying, this means the phase is varied and the amplitude and frequency is remaining constant. So let's see what does that mean. See here, if it's a binary PSK, the first signal phase is 0 degree and the second signal phase is 180 degree. What is phase? See here, this is a signal given here, and how the signal starts. Suppose that this is the wave here. Now see here, at this point the degree is 0, this point it's 90, and at this point it is 180, here it is 270, and at this point it is 360, or you can consider again from 0. So according to this, from where the wave start, it depends. Okay, so suppose that a wave is starting from this point, means like this it is starting. Okay, so its phase is 90 degree. Suppose that a wave is starting from this point, means like this it is starting, that means a wave is starting from 180 degree. So that's known as the phase. Okay, so here we will be changing the phase according to the data given. Here the first element is 0 degree, means if it's 1 it is starting from 0, and the second element is starting from 180. If it's 0, it will start from 180. See here, observe here carefully. If it's 1, it's starting from 0 here, and if it's 0, means if the data element given is 0, the phase will start from 180. Okay, as I mentioned you, the 180 phase signal starts from here. Okay, so it will be starting from here. Then the second one is 1, so it will be starting from 0. So like that we are altering the phase to represent the analog wave. That's known as binary PSK. Okay, bandwidth is same as the previous one, which is 1 plus d into s, and the second type is quadrature BSK. Okay, here we will have 2 separate waves. See here, we are separating the main wave into 2 parts. Okay, so by an oscillator we will be separating into first part and second part. In second part there will be a phase shift of 90 degree. Okay, and at last the wave will be rejoined. Okay, so let's see the process, what is used. Remember, if it's 2 bit only, then only we can do. Okay, means the first bit will be separated as a first signal, and the second bit will be chosen as the second signal. Okay, so the combinations are this. If you have 0 0, it will be minus 135. If it's 1 0, it will be minus 45. If it's 0 1, it will be 135, and if it's 1 1, it will be 45. These are the phase differences mentioned, just like how we have here 90 degree, right? In that way, if you have these combinations, we'll have the respective phase angles. Okay, so see here, the data given is 0 0 first. Okay, so we'll be separating the first wave here and the second wave here. This is the original carrier signal, this is the modulated one. Okay, this is the original wave which we get here, and after that we'll modulate it. That means if the wave is starting from 0 degree, it will start from 180 degree. Okay, so like that we are doing in the each case. Okay, here we will make from 180 degree, and rest of the things are same here, and then here also we will be doing the same thing. After doing both of these, we will check the data here. If it's 0 0, we will have to have the phase difference of -135. Okay, so the final wave will have a phase difference of -135. Then next one's data is here 1 0. See here it's 1 0, right? So here the difference will be -45. Okay, the phase will be starting from -45. Like that we will do for the whole wave here, and that's known as quadrature PSK. Okay, let's solve a numerical regarding it. Here we have been given the bitrate as 12 MB per second, and D's value is 0. The formula is same. R will be equal to 2 in this case, because each signal element will carry 2 data element. Okay, remember for PSK, R is always 2. Then we have to calculate the value of B. B is equal to 1 plus D into S. What is S? S is nothing but N into 1 by R. We have the value of N here, and R is also here. Therefore, we get the value of S here, which we will be using in this formula to get B. Okay, so B is 6 megahertz. Constellation diagram is nothing but by using a graph, we are representing the angle and the amplitude of the main wave. Suppose that the main wave is this. Okay, now we have separated in two parts. This is the first wave, and this is the second wave. Okay, now what does this graph represent? In this graph, the y component is the amplitude of second component, means the amplitude of this wave, means this height. Okay, that will be represented here. Okay, and the amplitude of first component, which is this height, will be represented here. Okay, this point. And after that we have the main amplitude here, x plus y. If we join it again, we'll get back the main wave, and the amplitude of the main wave is given here. Okay, by this line. And then the angle between the x-axis and the horizontal line is nothing but the phase angle of the signal component. So the phase angle of the main wave is given as this angle. Okay, the angle between x-axis and the hypotenuse. Okay, this is the last topic. In this we have quadrature amplitude modulation. This is nothing but it's a combination of a amplitude signal keying and phase signal keying. Okay, so by using the combination of both, we will get few types of constellation diagram. See here, this is the constellation diagram. Same concept, we are representing the wave which we get from the combination of ASK and PSK. Okay, so we'll get 4 types. When we use different types of schemes like unipolar or polar, or we use different types of levels like 8 levels here, or 2 positive levels and 4 positive 4 negative levels, like that we will get different types of constellations. Okay, so this is the diagrams for the constellations, and the bandwidth is same, which is 1 plus D into S. Okay.